Hello class, welcome to Pre-Algebra Lesson 1-2, which is all about understanding rational numbers. By the end of this lesson, you should be able to recognize rational numbers and write them in decimal form. So let's get started by looking at this graphic, and I'm gonna just move this a little bit, and I'm actually gonna make it a little smaller. All right, so there we go. So here you are going to see that we have several colors on the screen, right? And lots of boxes, circles, numbers. So let's talk about what this graphic means. And we're going to talk about this not just in this lesson, but in future chapters too. I just want to highlight a few things. So in my class, we have already covered integers. And something that you've learned with integers is that they are positive and negative numbers, but without any sort of decimal, right? So we've already covered, the basics of integers. Now, some of you have been wondering, like, what exactly is an integer? Well, let's talk about numbers in general. So in pre-algebra, we are going to look at something called real numbers. And you might be wondering, why on earth do we call something a real number? Well, the truth is, as you progress in math, you're going to learn about something called an imaginary number. And that's why we start using the terminology real numbers with you now, so that way when you get into future math courses and you hear the phrase imaginary numbers, you are able to differentiate the two. Okay, and I know when I say imaginary numbers, some of you are probably wanting to ask me some questions about that right now, like what on earth is an imaginary number? And if you are one of those people, come find me. We can talk a little bit. I'll give you a brief overview of what an imaginary number is. Okay, but for pre-algebra, let's talk just about real numbers. So over on the left, so remember this is our left, we're going to look at these circles, okay? So you can see the smallest circle there is something called natural numbers. Now, natural numbers are going to be your counting numbers. So let's say you played hide and go seek as a child, or you played tag where all the, or like the person that's it had to wait a certain number of seconds before they could start chasing. Usually when you count, you would go like 1, 2, 3, 4, all the way up until whatever number you guys had agreed on. And when you counted, you didn't start at the number 0. You always started at 1. Okay? So those counting numbers, those are your natural numbers. Then there's something called whole numbers, which is the same exact thing as natural numbers, except it also includes that number 0. So you can see 0 was added to the list. So whole numbers include the number 0. Then, if we keep moving our way out, now we're into that integers circle. And you can see, like with the integers, now we have the positives and negatives. And some of you might see the square root right here and wonder, why is there a square root there? We didn't talk about that. Well, it's because we haven't talked about square roots this year yet. But the square root of 49, if you were to simplify it, it's actually the same thing as the number 7, okay? So the integers are the same as your whole numbers, natural numbers, but it also includes the negative versions of those numbers. Then we have something called a rational number. Now, a rational number is anything that can be written as a fraction or as a decimal that repeats. So you can see like this one, you can see that the decimal portion repeats. It's 454545. Or ends. So if a decimal ends, so you can see like this one is negative 3.4. It doesn't have anything after that. It's just 3.4, negative 3.4. That is another example of a rational number. Now, that's what we're going to focus on, but I do want to mention something called an irrational number. An irrational number is a number that does not when you make it into a decimal, it does not repeat and it does not end. So usually that looks like this, where you can see like I have 1.2434871, and then there are these dots at the end of it. Those dots signify or show that the decimal is going to continue going on and on and on. And you can see with the decimal, there isn't anything that's repeating. So that is what would make this irrational. Okay. But like I said, today's lesson is going to be about those rational numbers, and this part of the chapter is going to focus on decimals and fractions. So today we're talking about decimals. So we have something called a terminating decimal. That's a fancy way of saying a decimal that ends. Okay, so like 3/4 is 0.75. There aren't any other decimals that come after that 75. So it's a decimal that ends. Then a repeating decimal is when you have something where, like in this case, if you were to type into a calculator 1/6 or use long division to calculate it, you would get 0.166666666, and then your calculator would eventually cut it off because your calculator is not powerful enough to just keep going on forever and ever. And when that happens, to save your hand from writing too much, what you do is we use something called bar notation, and that looks just like this. You put 0.1, and then once you get to the number that's repeating, or numbers, because sometimes it is multiple numbers that repeat, you put a bar over it to let people know that that number is going to keep going on forever and ever. Okay, so that's called bar notation, and that happens with repeating decimals. Okay, so now let's practice calculating some of them. So with our first example, we are going to calculate a terminating decimal. And with this terminating decimal, there are a couple of vocabulary words that I just want you to be aware of, not necessarily like that you have to memorize them. I just want you to be aware of them, okay? And they are dividend and divisor. So the top number can be called a dividend, or if we were to write it like this is your dividend, and then this is your divisor. So top number of a fraction is called a dividend, the bottom's divisor, or if you were to write it horizontally, it would still be the 52 or whatever that first number is, that's your dividend, or your second number is your divisor. The phrasing that you're going to hear me say most often, because when we're dealing with fractions, it's just the phrasing that is most common, is the phrase numerator for the top number and denominator for the bottom number. Okay, and you're going to hear me use that just because with the math classes I teach, that's the phrasing that I end up teaching the most. Okay, but when we are solving something like this, we're going to do some long division. So that means that you take your dividend and you put it inside the house, and then you put the divisor outside of the house. Okay, so it goes dividend inside and divisor outside. Now let's refresh our memories on how we do some long division, because it might have been a little while since you guys have done this. So what you do is you look at the number on the outside. So for me, that's 80. And I say, how many times can 80 go into the number 52? Well, or I should start with, how many times can the number 80 go into the number 5? 0. So I'd put a 0. Then I would look and say, how many times can 80 go into 52? Again, 0. Now it gets a little different because I see that I don't have any more numbers in the dividend or under that little house. So what I do is I add a decimal place to the top of the house and inside, and I add a 0. Okay, so now I want to figure out how many times can the number 80 go into 520. Some of you might be thinking, how am I supposed to know that? A hint I would give you is, since both numbers end in a 0, just ignore the 0 for a moment and think, how many times can 8 go into 52? 8 can go into 52 6 times. So 6 times 0 would give me 0, and then 6 times 8 is 48. So now I would subtract those two numbers. So I would say 0 minus 0 is 0. 2 minus 8 is not going to happen unless I borrow. So I'm going to turn that 2 into a 12. 12 minus 8 is 4. And then 4 minus 4 is 0. All right, great. We have our first number, right? Now I want to look and see how many times can 80 go into the number 40. And if I think about that, it can't. So I bring down that next 0. And I think, how many times can 80 go into 400? And again, they end in 0. So then what I would do is I would say, how many times can 8 go into 40? Well, 8 goes into 40 5 times. So now I would say 80 times 5 is 400 exactly. It works out really nicely, and I'm left with just a 0, which means no remainder. Now if I were to take this number up here and rewrite it, usually we just put 1 0 in front of a decimal point, and then we copy our number. So our answer would be 0.65, or if you were to say it with our math vocabulary, 65 hundredths, because that 5 is in the hundredths place. Remember, it goes tenths and then hundredths. So 65 hundredths would be our answer. If you have questions about that, please ask for some help. I'm happy to help you. Why don't you go ahead and figure out the answer for this fraction, convert it to a terminating decimal. Good luck. Okay, for this problem, hopefully you ended up at 0.875 or 875 thousandths. Okay. Let's now practice one where we should end up with a repeating decimal and figure out what we're going to do with an example like that. So we have the number 5/18 and we want to convert it from a fraction to a decimal. So again, just like what I've been doing, I am going to take the top number, the numerator, and divide it by the denominator. Okay, so 18 can't go into 5, so I'm going to put a 0, and then I'm going to add that decimal point and think, how many times can 18 go into 50? Well, something I'm going to do to just help myself is I'm going to quickly write down my multiples of 18. So if I just keep adding 18, this is what I would get. So 18 plus 18 is 36, plus 18 is 54, plus 18 is 72, plus 18 is 90, plus 18 is 108, plus 18 is 126, plus 18 is 144. So there's just a few of the multiples of 18, and I know I went through those really quickly. I don't expect you to have those memorized. I just took a couple of seconds before the video to calculate out those numbers, okay? So now, 18 can go into 50. It looks like this is times 1, this is times 2, times 3, times 4, times 5, times 6, times 7, times 8. So it looks like it can go into 52 times without going over. So it's really important when you are doing this, you are looking for the biggest number that can go in without going over. So now let's subtract 50 minus 36. I would have to borrow. So I would have 14 is what's left over after that first step. Then I'm going to add another 0, And now I want to think, how many times can 18 go into 140 without going over? Well, I see it goes into 126 7 times, but times 8 would be 144. So 144 is too big. So I would have to say it can go in 7 times. So now I'm going to say 140 minus 126. Well, that is 14. And if I were to keep going, it would be 140. So you can see that here and here, they now match, right? It would be the same thing where I would be stuck in an endless loop of just getting the same answer over and over, and I would be driving myself insane. Okay, right? I could just keep going. But thankfully, with repeating decimals, once you start getting something like this, you are able to say 0.27, and then instead of writing like this until my hand can write nothing else from cramping up, instead what I can do is I can write it in bar notation like I mentioned earlier, where I would just put a bar over that 7 to signify that that 7 is what is going to be repeating. Okay, why don't you go ahead and try calculating this repeating decimal on your own? Good luck. All right, for this problem, hopefully you ended up at 0.2 repeating. Okay, so there's the work on the screen of what I did. If you have any questions about that, please be sure to reach out for some help. I'm happy to help you. Let's move on to example 3, which is just recognizing rational numbers in decimal form. So looking at these, we just want to figure out, like, is each of these a rational number? So remember, in order to be rational with the decimal, it has to either be terminating, meaning it comes to an end, or it has to be repeating. Okay, so looking at this very first one, negative 6.382. There aren't any of these dots here to say, oh, hey, it's going to continue forever. So we know that it's not we know that it has an end, right? So I would say, yes, this is rational because it is terminating. Then looking at that next problem, letter B, negative 1.539981. And I see that I have this bar notation right here, and that tells me that it is repeating. Oh, I spelled notation very incorrectly. Let me try that one more time. Bar notation. I'm very tired. There we go. All right. So that bar notation right there tells us it's repeating. And since we know it's repeating, we know it is a rational number. So I can say yes because it is repeating. And then our last one, we have negative 0.43524982. And then we have those 3 dots telling us that it's going to continue on forever. And I don't see any bar notation. So that tells me that it's not repeating. So I would say no, this is not rational because it is not terminating or repeating. Okay, so that would be my answer for letter C. Now looking at this question, I want you to answer whether or not these are rational. Okay, so look at letter A, figure out, is that rational? Look at letter B, is that rational? Good luck. All right, for this problem, hopefully for letter A, you said yes because it is repeating. That bar notation tells us that that 3 is going to repeat forever. And then letter B, hopefully you said no because it is not terminating. There's those 3 dots at the end. And it's also not repeating. This one can be a little tricky just because sometimes students see that there is a pattern here, right? Like it's 1, 4, and then it's 1, 4, 4, and then it's 1, 4, 4, 4, and then it's 1, 4, 4, 4, 4. So you can see there's a pattern to it. However, it's not the same exact thing repeating each time. So that means that it is not repeating. Okay? Okay, so if you have questions about that or anything else from this video, please be sure to reach out for some help, and I am happy to help you. I hope you have a great day.